Hello and a very warm welcome to everyone. Today's video is going to be about work, energy and power. We'll be discussing the concept of work, how the concept evolved, and later on in perhaps the later videos we will also be discussing as to what is the use of the concept of work as in physics. So without much ado, let's get going. We are going to consider here a block of mass m moving on a smooth or rather frictionless horizontal floor with a speed u initially to your right, as you can see, and we apply on this block a horizontal force of magnitude F. Now once we apply this horizontal force of magnitude F, this block starts to accelerate at the rate A. So the block begins to accelerate with an acceleration A to the right, and this acceleration A of course is F by m. Now we are all aware of this equation, v square minus u square equals 2as. In this equation, let's substitute this magnitude of acceleration, which is F by m, and once we do that, we get the equation v square minus u square equals 2F by m times the displacement s. Now after having undergone this displacement s, we assume that this block has now acquired a speed v. So v square minus u square equals 2F by m times s. That's the equation we now have. What we do is we take m and 2 onto the other side of the equation, and when we take m and 2 to the other side of the equation, we get half mv square minus half mu square equaling f times s. Now we have on this equation two different quantities. On the right hand side of the equation we have f into s, and on the left hand side of the equation we have half mv square and half mu square. We give these quantities names here. F times s on the right hand side of the equation, we are giving it a name work, and v square minus u square on the left hand side of the equation, half mv square and half mu square on the left hand side of the equation, we're going to call them kinetic energy. So half m times the square of speed, this is a quantity that we now call kinetic energy, and F times s, that's on the right hand side of the equation, we call this quantity work, right? So we've given names to these quantities. Half mv square is now called kinetic energy, and F times s is called work. So we've arrived at a preliminary description for this quantity called work. On the left hand side we have kinetic energies, half mv square minus half mu square. Now half mv square minus half mu square is the change in kinetic energy. It's actually the final kinetic energy, half mv square minus initial kinetic energy, half mu square. So preliminary description of the ideas of kinetic energy and work. Let's move on now and fine-tune this concept. The next diagram that you're looking at is again the same block of mass m moving on the same horizontal surface with the same speed u to the right, to your right, and this time the force F that we have applied, it's a constant force, but now this force is acting at an angle theta above the horizontal. Remember that F sine theta, the vertically upward component of this force, is less than mg, so the mass is not lifted off the surface. There is a horizontal component F cos theta which causes this block to now accelerate horizontally, Initial speed is u, the final speed after moving a distance s is v. Now this time the acceleration is going to be f cos theta by m. So now the acceleration is f cos theta by m. So v square minus u square again equals to as, and we substitute f cos theta by m this time in place of acceleration. And again the same rearrangement, we take m and 2 onto the other side of the equation, and we get final kinetic energy minus initial kinetic energy equals fs cos theta. Now fs cos theta we will be describing as f dot s. It's a dot product of the vectors f and s. On the other side of the equation, of course, we have final kinetic energy minus initial kinetic energy, which is the change in the kinetic energy of this block. So the concept of work just gets a little fine-tuned. Now work is not simply f times s, it is a dot product of f and s. So slight fine-tuning of the concept of work here. We now move on and discuss the concept of work in a more general manner, in a more general context. We will now be looking at the concept of work with a variable force. So far we've looked at a constant force providing work, and now we'll be looking at a force which is variable in magnitude as well as direction. And let's see what happens once the force is variable in magnitude as well as direction. What we have learned so far is work equals change in kinetic energy. Will it remain the same when the force is variable or not? Let's have a look now at the next diagram. So now looking at this diagram where we have a curved path, the mass m is moving along this curved path from point I to point F, and the force F is now a variable force and it varies in magnitude as well as direction. So with this variable force now acting on the object, what we do is, since the path is curved, what we do is we divide this entire path into tiny little elemental displacements of ds each. So we have lots and lots of tiny displacements, each having a magnitude ds. And if you add up all those displacements, of course, you get the total displacement. Now, let's have a look at a particular tiny displacement ds. Now this ds, of course, is in the same direction as the velocity of the object, and we have a force F acting on it at an angle theta with ds as well as v. Now this force will have two components. One component is perpendicular to the direction of motion, that's F sine theta, and this only changes direction of motion. That means it's the centripetal force, and it's equal to mv square by r, where r is the radius of curvature of the path at this particular point. The other component of the force, F cos theta, is tangential, and this tangential component of force is producing a change in is causing velocity to change. Now this F cos theta, the tangential component of force, is equal to mass times the tangential component of acceleration, and the tangential component of acceleration equals the rate of change of velocity. So F cos theta we now know equals m dv by dt. Now what we're going to do is we're going to replace m into dv by dt by m into dv by ds into ds by dt. So dv by dt has been replaced by dv by ds times ds by dt, and f ds, we take one of those ds's in the denominator to the left hand side, we have f ds cos theta now equals mv dv. Of course, we have replaced ds by dt by v. We all know ds by dt equals velocity v. So f ds cos theta now equals mv dv, and therefore f dot ds equals mv dv. What we'll do is we'll be integrating both sides now. F dot ds, or f ds cos theta, on the left hand side of that equation is the tiny amount of work dw done in that tiny displacement ds. So that f dot ds will be replacing by dw, and when we integrate that dw, we get w, the total work. So the integral of f dot ds from point I to point f, that is the total work. Now remember, this integral of f dot ds is the summation of the tiny amounts of work that are done in all those tiny displacements of ds each. So first amount of work is f into the first ds times the cos of the angle theta there. So what we are doing is adding up all the tiny amounts of work along the path. So first f dot ds plus the second f dot ds plus the third f dot ds, and so on and so forth. So we are adding all the values of f dot ds all along the path. So first f dot ds, then the next f dot ds, and then the next f dot ds. We are adding them all up to get the total amount of work on the left hand side of the equation, and on the right hand side of the equation we are integrating mv dv. Now m being constant, it comes out, and therefore we integrate v dv from u to v, and this integral on the right hand side gives us half mv square minus half mu square, which is the change in kinetic energy. And on the left hand side of the equation we have the integral of f dot ds along the path, which is the total work done, and therefore the work done in this process, in this path, equals the change in kinetic energy. And this here is the work kinetic energy theorem, which is of tremendous use in all of mechanics. We'll be using it throughout your physics in class 11 and 12. And so this concludes this video on the description and derivation of the work energy theorem and the introduction to the concept of work. So more on the concept of work in the upcoming videos. We'll be taking up some examples on calculation of work, and those videos come up also fairly soon on this channel. Please do like, share, and subscribe if you're enjoying the videos from this channel. Also, if you're enjoying these videos, do comment. Even if you're not liking certain things about these videos, you want some improvement somewhere, please do share your feedback in the comments section. Thank you very much for watching this video. Let's meet again.